So last time, if anybody still has any memory of what we did before the exam on Wednesday, we have started so-called indirect methods for solving systems. Major problem with Gaussian elimination and whether we do LU decomposition or not is that there's a whole lot of calculations to be made. Something that we call O of n3, n cubed. So if n is the linear size of my system, the number of the unknowns that I'm looking for, there is order of n cubed calculations in there, which when you think that most of the reservoir simulation matrices of interest have at least million unknowns, and that's the good day, then million to the cube is a lot, and it can take a lot of time. So, and that's the first part of it, and second part of it is that we never solve a linear system to just solve it once and we're done. By the nature of being an engineer, you want to optimize the system, so you want to go and test a number of parameters to figure out what works the best for your solution. So you don't want to just go and do things once, you want to do it 1,000 times over the range of parameters that are of possible interest. Maybe injection fluxes, maybe pressures, maybe you name it. Okay? So in that sense, speeding up how long it takes to compute the solution of the system is very important. All right, so we started so-called Jacobi iteration that reminds of fixed point method for root finding. And this is an example of a 4x4 system. We had actually 3x3 done by hand. But essentially, what we've done is in first equation, I took x1 and expressed everything, left it on the left-hand side, and put everything else on the right-hand side. And when I do that, I get something looking like this. Okay? And then the same thing I do in the second equation is just that I'm using the diagonal element here, x2, and I express x2. And then x3, x4. And if I have n of them, well, I go for n times. So basically, when we do that, we have something that is a little cryptic here in terms of sums, but it looks like this. So what I will do is I will start with some start guess. In any numerical method, we need to that is iterating, we need to have an initial guess. If you don't know what the guess is, well, 0, 0, 0 works, though it's always a poor choice. But if you don't know, it can work. So basically, you then compute this right-hand side using that guess, that old guess. Okay? And you compute the new version of your x's, all of them. And we are solving a system, so in this case I have 4 of them. In general case, I have an entire vector of them, n of them. Okay? So basically my vector here, in this k plus 1, is basically the iteration as I'm going. So this is my new iteration. Xi's are all of my xi's. I have n of them in this vector. Okay? So this is basically expressing a vector, new one, k plus 1th one, in terms of the old one, which is kth one. Okay? The old, new. Okay? So we had that actually, this example. It can actually work. When it works pretty well. So what we did is in this 3x3 system, last time by hand we expressed x1, x2, x3, right? Based on everything that we have in the system. And then I plugged in my first initial guess was 0, 0, 0. So it's a vector. I have 3 of them. And that's the guess that I plug in here into the right-hand side. So first time around, it's really easy because it's all zeros, right? So we did the calculation, and we already got pretty close. The true solution for this is 3 minus 2.5 and 7. Okay? And I'm already starting from a very dumb guess, 0, 0, 0. I got to 2.62, that's pretty close to 3. Okay? Minus 2.76 and 7.14. Okay? It's pretty good. So then on next iteration, I think it was, the bell was ringing as we were computing, so we would get even better. So hopefully I can actually get close, pretty close, within 4 or 5 iterations. And in that case, it's way less of calculations in terms of number of calculations that n cubed, which in this case would be 3. Okay? So that's a definite benefit in terms of any kind of round of error that could pile up. So let's actually now go. And one quick question for you. So when will I stop with this?
You could do the approximate error when the change is very negligible.
So I have this old guess, which is a vector, and the new guess, which is another vector. So what do we use for that? Add them together, okay? But we did something to measure vectors. What did we use to measure vectors? Norm. So I could do norm of the difference. Which norm? It's your choice. Okay? So either of them works. We have 3 options. Okay? So I take a difference between these 2 iterations. We always look at difference between 2 iterations, right? So I take the difference and I can do L2 norm, if that's what you like, which is basically Euclidean kind of a length of this difference. Okay. I could do L1 norm, which is just add up absolute values of this difference. And I could do max norm, just look at the worst case, right? The largest one, and see how big it is. If that largest one is small enough, I'm good. Which one works the best? Kind of depends on the situation. Practically, in these numerical methods, look, things are either converging or they're not. The norm in which you measure this convergence and how close you get to the result is going to slow you down by 2-3 iterations. Not a big deal. Not a big deal. That's not the crucial thing. The crucial thing is, are you actually going to, starting with some guess, get to the solution, or are you just going to spiral out and get something continued? So we do actually have convergence criteria for this method, and it's somewhat similar to our fixed point method. If you remember, in fixed point method, the g prime x is equal to g of x, and then you have a g prime that has to be small. Right? It has to be smaller than 1 in absolute value. Here it's not directly obvious, but an equivalent of that is that my matrix that describes the system is diagonally dominant. And I'm not going to go into the theory of why is it so. There's a proof that you could do. But basically it comes down to so-called diagonal dominance. So all of the elements on the diagonal of the matrix, when I take each element, it should be an absolute value larger than the sum of the rest in that row. Which when I go back to my matrix, 3 is larger than 0.1 plus 0.2, which is 0.3. 7 is larger than 0.1 plus, this is actually kind of obviously designed to be that way. So 7 is larger, this is a class example, it's always pretty. 0.1 plus 0.3, okay? And 10 is larger than 0.3 plus 0.2. Not just larger, but of a different order of magnitude, okay? So this one, that's why it converges so quickly. Yes?
Okay, I was just going to ask, that's the criteria for convergence?
Yes.
Okay.
So with that, it's guaranteed. If it's not present, maybe it works, maybe it doesn't. Okay. This is an easy sort of visual check for the matrix to see whether it's not. Otherwise, we have to go through different analysis, which is not so easy. It's actually then easier to go try solve the system. All right. And then this is the comment of like, when are you done? This case basically says, well, give me a tolerance, and then all of the differences between coordinate by coordinate difference in relative ways. So we always look at the relative error should be less than tolerance, which is essentially my norm 1. Or maximum norm, however you look at it. So the choice of the norm, we can actually use norms. So that's, you can use norms as programmed in Python. All right, this brings us to computational assignment. Yeah. So you will create a function, Jacobi iteration, so open up Python. And it takes a, b, x0, x0 being initial guess, and some tolerance, and does this Jacobi iteration until tolerance is satisfied. So I'm going to start you off, and then we're going to work on it in class. So here, I was doing this by hand. So I actually did here, whatever I was doing by hand, I typed it into Python. So this is just taking my new iteration in terms of an old, starting from 0, 0, 0. So this is digital version of those notes that I've showed you.
Is it on Canvas?
This one is not, but it can be in a second. If you want, it's just by hand. I didn't do anything else, so. Do you want it? You do? Sure. Then let me actually then start you off, so then do define Jacobi iteration. Right? And you're gonna provide a, b, x0, and tolerance. And you're gonna return what? X for now. We're gonna call it x. And maybe that needs to be modified. So basically, this is the function that is going to do this iteration by hand, just in a more structured manner, right? All right, excellent. So I'm gonna, this is what I'm gonna save and share. Canvas.
X naught is a vector, right?
X naught is just like, yes, a starting point.
Oh, is it just 1 point?
It's a vector, yes.
Okay.
A starting point for iteration,
Okay.
but it's a vector. So bad choice of words. Initial guess, let's just stick with initial guess. Yes, it's uploaded. And again, all I did is I got this zeros. So basically, this is in terms of old, and this was just for that very specific system. What you want to focus on we do remember how sums look like, so you just focus on it. And Ningyu and I will walk around.
While loop or no?
Yes, while loop. When is that while loop going to stop?
Errors.
When my error
Less than 1.
is less than, what did we call? What did I call? Tolerance. TOL. If you want to call it EPS, by all means. So let's type in what we know. What is error? I don't know now. I'm going to initialize it. With what? Well, 10 times tolerance. And then I'm going to do while loop. While your error is less than tolerance, do something.
Wait,
How larger than? That was a test. What's also a good idea, I already know, or I hinted that this thing might not converge. So I might want to count the number of iterations and give myself a maximum. So let's just do, this is kind of what I would call mechanical parts that are always the same. I'm going to say 10,000 is plenty. An iteration to start with is 0. So this is just to guard yourself from infinite loops, which when combined of this thing sending information to your web browser can stop your computer. When something bombs and you have additional software layers on top, never a good idea. Okay. So I have x0 coming in, so I don't have to do anything about x0. You have to make x new based on the x0. Do you want to call this x old? Is that easier? Since that's what I was typing in here. Okay, let's call it x old. So to initialize things, I need some space for x new. That might be a vector that is 1 million long. Better find some shelf space. How am I going to initialize x new? Into zeros. And you haven't, if you haven't activated this cell, now is the time so that you import NumPy of x old shape. Right. Now, conceptually, compute x new values based on A, B, and x old. Then update error based on x new and x old. And then update x new. That's all. Yeah, this is sort of what we always do. This could be a root finding method. It is actually, of sorts. It's just that the equation is linear. Oops. And actually, one of these days I'm going to learn how to type, but not today. So how I update these new values, k plus 1, in terms of all values, k is given here.
Let me go through the eyes without like a for loop.
You still need a for loop.
Oh, you still need
While
for
loop is on the outside
Okay.
to kind of embrace this vector, new vector, old vector, right? I got a computer vector. I have to compute every value of that vector. Okay? There has to be a for loop somewhere. Actually, that some hints, I have a sum in terms of j's. There might be a double loop. Nested loop. I think now you see why in exam 1 we had these sort of examples to implement in Python without knowing what they were really. X new of I. This is X old of J. These are my AIJs, B of I. if this happens for every I, for every I, try again, for every I, and then I'm summing for every j except for some of them. Some sort of an if check should be in there. Yeah, we're doing
I can write.
prepared. You could. We actually test the paper. For every I.
I don't know if this is the right range, but if you can put something
For I in which range?
use some too.
The J one, but it has two starting
J one has a
points.
sum.
One is the starting. I'm not sure you're right. For J is
No.
right.
Yeah.
So I have n elements.
It might be, it says 1 to n.
Right?
So it's 0
So
to n
for one
minus
thing,
1.
you need to know how big is your x. Okay? Yeah.
What is my I range? Is that right?
Now what?
I.
X mu.
No, it's also.
X mu y.
I was just going to use the formula. But I just didn't.
Yeah.
Oh, we just use for.
The second
Mu
formula.
y minus a weird sum. Oh, it's a weird sum for now.
Right? The second, or something, because he says if J is
So mu y minus that sum divided by
I think it's either in between or after the J.
Does it make sense? Does it look familiar? A of I.
Yeah, that's what it is. J is like, where is that? J.
I
It's gotta go.
It's got no to go after the J, because you're not gonna have the, you're not gonna have a J.
Transcribe half of it. Now that sum is some sort of a sum. Compute that sum.
Yeah, so it's like,
If it's a sum, you're starting at
n is
zero.
like, say n is 0, not equal to 0, and then, that means, oh, so that means.
You can do that, yes. I never do it because I never do it because I'm writing on the screen. It's hard to see.
That's.
But otherwise I'm writing it.
That's my major.
J is not equal to y, so you're skipping that one. So J is equal to y,
But you have to do this.
or you say J has to be bigger than y. However you want to do it. Test somehow. And we're testing with if. Or restrict your formula.
I don't know why there's a K there.
Could just be.
Let me start off those that I cannot. So I'm really, I already gave you a formula to implement, right? I have to do this to actually fill all of the vector values. I have n of them. Okay? I have to do this for all n. When I know how many times to do something or repeat something, then I use a for loop. So I'm going to fill in the values. So I'm going to say for I in range. Which range? I have a vector of certain length, right? Well, length of this x old or x new, either way. I don't. This is it. I could start from 0, if that makes you feel better. But it's the same. I do actually start from 0 because then visual check is faster. Okay? But that's a personal preference. So now this rule, I'm literally transcribing a formula in Python now because I gave you the formula.
It does nothing.
So how am I calling this k plus 1 iteration? That's my new, right? And I'm focusing on computing all of the x new values. So my x new of I is equal to what? B of I minus some sum. And you know what? If I don't know it, just write down S. And then focus on computing that next. So low-hanging fruit first. B of I minus S divided by A of II.
This is for a single element of X nu.
Yes. For single element of X nu. But that's what my for loop does. So that's essentially, so X nu is B of I minus S divided by A of I. And for now, I don't know what that S is, so well, write down S is equal to 0. And that's how I start sums anyway. So this is this approach, like type in what you know. That sum looks scary, well, write down S and then focus on that next, kind of split your problem into smaller ones. So then I wrote this correctly. So X nu of I is B of I minus this sum, whatever it is, divided by A of II. And I can just quickly compile to see that that works, or right? So that I didn't have typos in the way I call the matrix element and things like those. Well, it didn't complain, so I did something, right? I didn't. We're gonna do testing next. Okay, so now let's compute this S. Any questions so far? Did everybody catch up with me? So this sum loops over basically all of the elements in the row I, right? Except for the diagonal element. That's this one, because that's the one that we left on the left-hand side. Everybody else went to the right-hand side, right? Right? All right. So I have to have a for loop that goes through all of the elements of my old, X old, right? And there's n of them. And I gotta skip one. So I can skip that one by testing with if. I can write down 2 for loops, up to I and then after I. Up to you, really.
Why can't J equal I?
Because that's already here on this side. So when we were creating this, excellent question. When we were creating this, then we left this II on the left-hand side and expressed, and everybody else went to the right-hand side, so that I don't have that II element on the right-hand side, okay? Everybody sees that? That's basically how the method was designed. So I gotta skip it, otherwise I'm gonna introduce an error that I'm not gonna be able to recover from. Then you're gonna not converge all the time. Okay. Right? Okay, so this S is another for loop. And you know what? I like calling these things N, so I'm gonna do that. So for my J, let me compute this sum. Indent 4, don't forget that. S is S plus A of IJ times what? My old value X old of J. And all of that happening if, I don't need it, I different from J. Everybody agrees with me? Of course you do. Even when I'm not correct, you do. I'm here genuinely asking for a checkup. I should ask Lingyu. Lingyu, do you agree with me? All right. Save. So let me just go back to the formula. And that's all I did. I just went through all of the i's. Yes, we have to shift to 0 because this is Python. We go through all of the i's and we check that this is different, that ing, yes.
What is the K in the formula?
That's my old new.
Oh.
What the error?
So now computing the error. So hopefully I computed something. What's the error? Oh, this is new or y. See, nobody said anything there. So this is I computed my x new values. So now I have a vector x new and the old vector. I gotta figure out how different are they, because I stop iterating when they're not very much different. And I measure that with norms. That's what norms are for. So my error, does anybody remember how to compute the norm? I could do it by hand. I could use something that NumPy has. You can do it by hand. Linealg dot norm. And let's just do x old minus x new minus x old. So I agree that you can compute it on your own. That's not the point of this exercise, so we're just going to use what's there. Plus, it's kind of a cleaner code, a little cleaner code. Otherwise, I would have to have a for loop. That you can say comma 1 if you want one norm. This way it's going to be two norm. Again, either way, thing converges or it doesn't. There's a small difference in the number of iterations you're going to do. Nothing to write home about. Dear mom, my L2 norm did not converge in the same number of iterations. My L1 norm, oh my. And my mom writes back, I don't care. As long as it converges, my dear. Anyway. Okie doke. And now I need to update my x new. Can I just write x new is equal to x old? I should be able to, but we said that that practice is a little bit dangerous for vectors. So we're going to use empty copy instead, in which case the values will be literally taken over and copied in. Did everybody understand that cryptic message from Ningyu about 10 days ago on Canvas?
Oh, yeah.
Oh, yeah. One person did. Okay, great. Well, let me explain. So basically, when I have all of these things are in memory, you can imagine a little shelf in a memory where all of these things are stored. And you can get to that memory by its address, literally. Where is the start of the array? And then you go and start meddling with the memory next to it. Okay? Or you can literally go and take values and pass just values, create a copy of something else, a temporary copy, and then pass it. So when you're giving things to functions, often, you will actually not create an extra copy, which is what you are mentally doing, but computer might not be implementing it that way. But you're literally going to just give the memory address. And then computer just goes to that memory address and meddles with that first row, whatever is in the first row. So next time you come to that memory address, you see that change, even though you didn't intend to do that change. So if we want to prevent that, then possibly it's a better idea to just say NP copy of X old. That way, I'm just taking extra version of values and placing them wherever it is that I'm storing X new. And both of them remain separate shelves and stored in separate pieces of memory. Okay? Because danger here, if I just say, well, let X new become this new address, then I might meddle with these values here, and they all become the same instead of different, and that can be problematic. I might just immediately implement Gauss-Seidel without knowing it. And that's a different method, yes. Yes, it should. That was a test, too. Me talking and writing code at the same time, always dangerous. All right, I'm not a parallel machine. Is this it? I did all the steps. Now let's just hope that it works correctly, right? So how do we test? I already shared this version. Oh, I didn't. I gotta type it in. Oh, well, we will type it in. My A is NP array. So it's 3, comma, 3 is the only thing I remember. Minus 0.1, minus 0.2. Next row. 0.17 minus 0.3. And then next row. 0.3 minus 0.210. Okay, that looks good. And then my B, $7.85 minus 19.3 and 71.4. And then X old, the starting value, NP zeros of the shape. And my X is, it's going to be a problem here. What am I returning? I should return something that I actually computed. That'd be nice.
And the maximum number of iterations.
What maximum number of iterations I set to 10,000, for better or worse. But I need a tolerance. It's not running? Uh-oh. Mine is not running either. All right. Something here. X new is not set correctly. Did I override? Something was sitting in the memory, I believe, from the previous one, so now it is. Now I just have to print the result. Pretty good. So there was a problem if you only had this executed and you did not execute this cell where you define the function. Then the previous version of X new was messing with whatever we used here. Just make sure to execute all of the cells. Did you get something like this? So here's one update I could do to this. I could be greedy and recognize that once I'm, let's say that I'm at xi, let's say that I'm computing x7. By the time I reach x7, I already have 6 values previously computed of these x's. So Gauss-Seidel method says, well, use these updated values. Don't use x old, use the new stuff. Okay? It's called the greedy algorithm. So instead of using my old version, just use the new one. Fair enough. And that can be sometimes faster. Guess what? This is going to be your homework assignment to modify this code that I'm going to post, just in case you didn't do it correctly. And basically then compute from there. Yes? Was that, are you just here? All right. So that's called Gauss-Seidel. And another version could be that you take a little bit of that old value and a little bit of new value. So you compute this new the way you would in Jacobi method. And then instead of using the new value, you use a fraction, let's say 0.2 of old value and 0.8 of the new one, or whatever other combination mixture. Okay? And that can actually behave better or converge faster in certain cases. And you're actually going to test that. That's called successive relaxation method, where you take a lambda times new value plus 1 minus lambda times old value. So your next homework that is already posted will have a component to modify this code and actually test that. And one final, yes?
So our homework is to create the relaxation method.
Yes, so your homework will be to modify the code to do Gauss-Seidel, as well as this. I'm going to post this code, so modify this code into 2 different other methods. After Thanksgiving, yes. I was just wondering. Homework, yes. Yes. That was posted. I don't want you to be, bored after Thanksgiving dinner. The best thing is to program. That's the best way to process turkey or mashed potatoes or both. Okay? And then we're just going to comment on norms for matrices next time. All right. So can I test that Fortran thing, Dr. Olson? Dr. Olson was supposedly writing in Fortran. Can I test that? That's a quiz.